Hi, everybody. Welcome to the UCL Electronic and Electrical Engineering Spring into STEM lecture, hosted by Dr. Antonio Lombardo, entitled 2D Materials for Next Generation Electronics. We are just waiting for people to join, and then I will pass on to Antonio to commence. Thank you.
Right. Good morning, everyone. It's very nice to give this talk for the Spring into STEM. So today we are going to talk about 2D materials for next generation electronics. So let's start by defining what 2D materials are. So 2D materials are materials consisting of stacks of layers, each layer consisting of just a single of a few atomic thin lattice. And it is important to distinguish the bonds in plane and out of plane. So within each layer, there are very strong covalent bonds, and there are fully saturated surface bonds. And what is very important is that even in the form of a single layer, these materials are stable. Out of plane, the bonds are very weak, and the individual layers can be easily separated. I think a good way to understand the structure of layered material is to think about a book. So a book consists of many pages. So if I try to stretch an individual page, I will find quite a lot of resistance as an effect of the strong bonds in plane, whereas when I try to separate pages in the vertical stack, the bonds are very weak. So that's very much the similar picture. The most common layer material and corresponding to the material are graphite and graphene, which are the material that we found in common pencil. So if I imagine to use a pencil and just look at the trace that I'm leaving, if I take a microscope image of the trace, I would see something like this. And that gives me an idea how this graphite consists of many different crystals that are very easy to slide one on top of another. And that's the reason why I leave a trace when I slide a pencil on a page. If I were able to zoom within each of these crystals, I would see a structure like this. So a number of individual layers of carbon atoms, each only one atom thick. And that one atom thick layer would be called graphene. Let's look a little bit of the history of 2D materials, starting with a little bit of fun. So like a lot of very nice stories, it starts with the legend. So the legend says that in 1565, near Grey Knotts in Cumbria, there was a storm, and a storm managed to uproot a tree. So when the tree fell down, there was a shiny black substance close to the roots, which we now know being graphite, but at that time was thought to be a form of lead, and indeed they call it plumbago. So the locals really started to make good use of it for a very important application. So they noticed immediately that material was very good to write. So it's very likely that the very first 2D material has been produced on the fur of a sheep. And just, I'm an Italian, so I need to mention that Italians then added a little bit more style by introducing the wooden holder. And it took almost 3 centuries to have the razor, which was invented just in 1858. Right, now let's be a little bit more scientific. Let's look at the scientific history of 2D materials. So 2D materials are not something very new, at least as building blocks of in theory, they're very well known. So already in the 19th century, graphene was being exfoliated down to very thin crystals. The entire band structure of graphene and graphite was calculated in 1947, and in the 60s there were even some early reports of very thin layers of graphite. But what really made the difference was in 2004, when Andre Geim and Costa Novoselov published a paper in which they investigated the electric field in atomically thin cardboard films. And this paper was really a game changer because, first of all, it showed that it could be possible to extract individual layers from a 3D structures. These layers were stable under condition. Just out of luck, they found out that despite being a single atomic layer, it was possible to see these crystals just using a very standard optical microscope. And what is more important, and most important of all, is that they investigated electronic properties. And the electronic properties of such materials were quite remarkable and very different from the ones of conventional semiconductors. So this experiment was incredibly important, and for that reason, it was recognized with the Nobel Prize in Physics in 2010. Now, we don't really have a lot of time to go into details, but just if you want to understand a few of the key properties of this material that was extracted, which we have called graphene, is the fact that electrons move faster than any other material, what in electron we would call electromobility, can sustain current densities orders of magnitude higher than metals, optically speaking, can absorb any wavelength, is stronger than steel, is flexible, is bendable, and it's also a very good conductor of a very good thermal conductor. So there are a number of properties that are associated with this material. And indeed, since the groundbreaking experiment, there is almost 20 years of very intensive research. And every time there is something very new and very interesting coming up. So I said that we are dealing with 2D materials. So let's try to define how thin 2D material is. So let's put things into scale. Let's start from a human being. So about 1.75 meters. So we are in the order of 20 billions nanometers. As we go down in size, let's look at the fly, 10 million nanometers, air, about 75,000. The smallest thing we can see with our eyes, about 10,000 nanometers. If we go into the microscopic world, we can look at bacteria in the order of 1,000 nanometers, transistors, tens of nanometers, DNA, 2 nanometers, graphene 0.3 nanometers. So really, these materials are among the thinnest things you can possibly imagine. Let's try to think how many materials exist. So 2D materials are really a large family. Graphene is probably the most well-known, but there are lots and lots of them. So apart from graphene, probably the second most important class are the transitional metal hypochrogenides, such as MOS2, WSO2, and so on. There are 2D insulators like HPN, there are chemical derivatives, there are really a lot of materials. And what is important is that despite having a similar structure, the properties are very different. If we just focus on electronic properties, we range from semi-metallic behavior like graphene all the way to insulator such as boron nitride and passing to semiconductors like black phosphorus or hafnium disulfide. No one really knows how many 2D materials exist. However, some theoretical calculation suggests that there are probably about 2,000 of such materials. So now that we have understood what 2D materials are, let's look what we can do with them, particularly for electronics. And to do that, let's look for a second what is the fundamental building block of modern electronics, which is the field effect transistor. Field effect transistor is a 3-terminal device consisting of one control terminal, which we call gate, and that terminal controls the flow of current between the other 2 terminals, which we'll be calling source and drain. As simple as this really the basic of more or less everything we do in electronics. Indeed, for example, if you look at computation, field effect transistors are coupled to form digit circuits, so logic gates working on Boolean algebra. Then these gates are combined together to form building blocks, such as memories. then different building blocks are combined together to form microarchitectures, and eventually that's the interface that we see when we use a software. But all essentially the most fundamental component of all electronic is the transistor. So transistors have evolved in the last few decades, so their performance has increased massively, and that to a large extent is due to the fact that they've been made smaller and smaller. So essentially it is due to miniaturization. Miniaturization increases the packing density, increases the circuit speed, reduces power dissipation, and also reduces manufacturing cost. All in all, this effect is expressed by the so-called Moore's law, that says that the number of transistors in an integrated circuit approximately doubles every 2 years. And this was an observation done in the 60s and has been proven incredibly accurate for decades. However, there are some limitations to this process. So when we scale down the transistor to very small sizes, there are new phenomena that are happening, and basically we cannot simply keep going with the same structure. And indeed, the semiconductor industry has come up with new solutions. First of all, reduce the thickness of the channel, then to move towards three-dimensional structure, and in particular the FinFET, which is the current technology, and then is moving towards what is called gate all around, so where there are nano sheets which are surrounded by the gate. However, there are some limitations in what we can do with conventional semiconductors. In particular, there is a sort of boundary which is approximately 5 nanometers in thickness, which is the critical dimension below which some degradation of the material starts to happen. And that's where 2D materials really can play a significant role, because then we can they can scale down without the limitations, without the degradation that happens in conventional materials. And we can see, for example, an important parameter which is called electromobility, and we can see that two-dimensional materials already in the very early stage of research, they are significantly better than conventional semiconductor. And indeed, it is predicted that 2D materials could sustain this scalability of conventional semiconductors. That's not the only approach, because electronic faces another very important problem, which is energy consumption. So there is a parameter which is called subthreshold swing, which essentially means the amount of voltage I need to provide to the control terminal to increase the current of a factor of 10. And that is not a technology based, it's not a material based problem, because it's fundamental to the way we manipulate charge carriers in transistors. So another approach is to switch to a completely different technology and go into quantum mechanical tunneling. And in these two-dimensional materials already proven their potential, because there was this very important work called Atlas TFET, in which a factor almost of more than 10 times reduction was achieved, and also a factor of 2 into several decades. So very, very important results. And finally, I also would like to mention that 2D materials can also be used for neuromorphic, which is a completely different approach to computation, which is inspired by the brain, and that requires new hardware. And that's because the way we perform computation, in particular computation for artificial intelligence, is incredibly energy inefficient. While neuromorphic takes inspiration from the human brain to combine memory and logic in a single unit, which in the case of neuromorphic is typically represented by megisters. Finally, I would like to remark the fact that 2D materials can be easily combined, and that's stemming from the fact that they don't have you don't have to match the lattice constant between the layers, so you can make materials on demand. And finally, in terms of technology, 2D materials are completely compatible with the so well-developed semiconductor technology. For example, graphene has been already used in integrated circuit, and so as MOS2. So, in summary, I hope that I managed to show you that 2D materials are a large family of materials with a large and often unique set of properties. They are potential for different new generation electronics in terms of scaling, in terms of power consumption, also in terms of changing completely the way we do computation. They can be combined into heterostructures, and they are compatible with semiconductor technology. So thank you very much for your attention. If you want to hear more from our research, these are our contacts, and I'm ready to take any question. Okay, so I'll start from a chat, sorry, from the Q&A. I can see there is already a question saying, are there any commercial or upcoming in development electronics or project that use 2D materials? If yes, what examples are there? So I think we need to distinguish what sort of electronic we are looking at. Because these materials can fit into integrated electronics, which is very much what I've been discussing, but they can also be in the area of flexible, stretchable, wearable, and so on and so forth, which have completely different set of requirements. So when it comes to integrated electronics, I think the performance are there at the level of individual devices. There is a lot of effort in scaling up the technology. Just to give some figures, the European Union has invested 1 billion euros into 2D material, and this year is when the first pilot line has been launched. So there are big companies like IMEC, for example, which is a major semiconductor manufacturing research center, that they are developing all the technology required to bring that performance from an individual device to a microprocessor, to something with a large number of devices. That also is linked to production, which is something we really haven't had time to talk about. The production of these materials has also made an incredible progress, because in order to have a real sort of wafer scale application, you need to be able to produce materials on a large scale with uniform characteristic, reproducibility, and so on and so forth. So there is a lot of effort being done there. So long story short, there is a lot of work in progress. There are already some commercial products. For example, there are companies that are using the property of graphene of absorbing light of virtually every wavelength to do what they're called hyperspectral sensors. So yes, there are some commercial products. There is not a 2D microprocessor yet. Okay, then the second question is there any position UCL related to 2D materials? I'm not sure that's exactly the scope of this seminar, but I guess the short answer is yes, there are positions available. So if you're interested, just get in touch. We can discuss separately. Then there is another question that's very interesting, which says, what causes the superconductivity on 2D graphene? That comes from, let me go back of a couple of slides. So that comes to this ability. So if you take a single layer of graphene, that one will not be superconducting at all. However, if you take 2 layers of graphene, and then you very carefully control the stacking angle, and that results in what is called a moire pattern. So basically the 2 layers will be interacting, and there will be a periodic modulation of the potential. So it is only in this condition and a particular angle, which is called the magic angle, that you will be able to achieve superconductivity. So it's not a single layer, it is an effect on the interaction of two individual layers at a very particular angle. Next question is, we know the latest CPU has reached 5 nanometers and even more. How soon or can we use the CPU into the materials? Right, CPUs are incredibly complicated structures, and semiconductor industry is probably the most conservative industry that exists. So I think we are at the stage of the proof of concept. So I would imagine that we will see 2D microprocessors in research. So if you want 2D CPUs in research within a few years, I think to see that in a commercial product, then it will take much longer. Also because it's not just a matter of performance. As I mentioned, there is a matter of production, doping, contacts. There are a lot of factors that have to be taken into account to make this technology to become a commercial technology. I don't see any other question in the chat. Is there anyone who wants to ask a live question, perhaps?
I think that may be it, Antonio. Thank you.
Okay, wonderful. It's been very nice giving this lecture. Thank you very much for this opportunity, NAFTA, and thank you very much for all the people who attended.
Thank you, everybody, for attending. Thank you, Antonio.
Bye-bye. Thanks.